So now we're going to talk about hybridization. And to do this, I'm going to really just lean on these visuals I have here. Um, so this is all straight out of your textbook. These are textbook figures that I have made available on the Moodle page, but I'll just be kind of mousing over them and talking about them here. Again, it's stuff I can't really draw on a board, so that's what we're going to be working with. And so we're looking at the hybridization of carbon. And before we get into what this figure is, um, let's just kind of talk about what it's showing here and what hybridization is. And so hybridization is going to be when we mix atomic orbitals. And so that's why what we're starting out with here are our atomic orbitals. And so these are just the valence electrons in carbon. And so we have 2 electrons in the 2s orbital, and then we have a series of 3 2p orbitals, and 2 of them are half full. So there's 2p electrons in carbon's valence shell. And these are organized by energy. So the 2s orbital is lower energy than the 2p orbitals, which are degenerate. They are equal energy. But we can kind of remix them into new orbitals, and that's what the idea of hybridization is. And so we say they become hybridized, and we get these we call sp3 orbitals over here. In the case of carbon, we'll talk about a few other situations in a little bit. And what happens is that these remixed orbitals energetically land somewhere between the high of the atomic orbitals and the low of the atomic orbitals. So somewhere between the 2p and the 2s. So it's more energy than a 2s by itself, but it is less energy than 2p orbitals. And these are all degenerate. These are all the same energy level. And so it hybridizes. We form 4 molecular orbitals. So now these kind of correspond to, well, I shouldn't say molecular orbitals. So that's a different thing we talk about later. So it forms 4 hybridized orbitals. I got to be very careful with my language here. And they're going to end up being half full in the case of carbon, which makes sense for carbon if you think about it. It's going to make 4 bonds. It's going to need to pitch 1 electron into each of those 4 bonds. So all of the electrons are going to get split up and sent off into bonds. And how does it do that? Well, according to hybridization theory, it makes 4 new orbitals that each are half full, and so each of these are primed to be used in a chemical bond. And so what does this look like in 3D space? Well, that's what the bottom of this figure is for. And so we look over here, it's showing the same thing as up top, but now it's showing it in space. And so we have our 2s orbital, and then inside of it we have our 2p orbital. So they're actually, inside of the s orbital. The s orbital is a little bit bigger. And there's 3 of them. So we got a PZ that goes along the z-axis here, so it goes up, down. This x-axis goes, we say left, right, so we have px, and then py goes front, back. And so that's how we have our 3 different p orbitals. They're the same shape, but they are different orientations, and they don't overlap with each other. That's a key thing to remember. But what we're going to do is we're going to kind of combine these. If you're going to take linear algebra, or if you've ever heard about linear algebra, it's that kind of idea. We're going to sort of add them all together in a way where what we end up with are these sp3 orbitals. And this is what they look like in 3D space. So again, they don't overlap each other. And then there's 2 kind of key things here about hybridization theory. And the first is that we get these new orbitals, and they're going to configure themselves in a way where they're going to maximize overlap with a neighboring atom and its orbitals. And then the second thing is it's going to match the geometry of our molecule. And so this is a technique that's used to explain geometry. It does not work for anything having to do with the energy of electrons. It's not going to help us out with spectra or absorbance or emission. It's not going to work with that. Magnetism, it's not going to help there. That's all going to come down to molecular orbital theory at the end of the chapter. So this is just kind of a first approach, and it's in line with what the top of the line computational approaches are today. It's a similar idea. It's just a very, very simplified approximating approach of it. But what it does do is it does give us the geometries. And so, if you look at something like CH4, if we want to make CH4, which is what we're seeing in this figure here. Well, the hydrogen isn't going to hybridize its orbitals. It only has one orbital. It can't mix things up. And so it's just going to have a 1s atomic orbital that it uses in its bonding. The carbon, so things with p orbitals, and we'll talk a little bit about things with d orbitals as well, are going to be able to mix up. And so these 1s orbitals of hydrogen, which are half full, they pitch one electron in. These sp3 orbitals that are half full pitch one electron in, and we get a bond. And valence bond theory says we have a shared area here. That's where the electrons are going to hang out, and that's what's going to hold this together. And we see that in 4 locations, and that gets us CH4. So this is the case with hydrogen. So it has only one electron in each of these sp3 orbitals, because again, where does the notation come from? I forgot to say that earlier. Well, we have an s orbital, and we have 3p orbitals, so it is sp3. So this 3 doesn't tell us how many electrons are in the orbital, it's actually the name of it. In the case of carbon, there are 4 valence electrons. There are 4 electrons in these orbitals. All right, so let's kind of carry over and let's look at 2 other elements that do something similar. So nitrogen and oxygen. We're just going to have more electrons involved. So nitrogen will still form sp3 orbitals, and so our 2s and our 2p orbitals will hybridize, make sp3s, but now one of them is full. And so that's our lone pair on nitrogen. So it generally makes 3 bonds with a lone pair. Well, that full sp3 orbital, that's our lone pair. Okay. And so if we make something like ammonia, NH3, well, we'll have nitrogen with its sp3 hybridized orbitals. These will all be 109.5, well, except now this one would, again, this breaks down a little bit because this doesn't account for the fact that this orbital would actually get larger with a lone pair. So it's not perfect, but it's a good step towards explaining the geometry. And so we'd say nitrogen is sp3 hybridized right here, and hydrogen is still just 1s orbitals overlapping with it, and we get NH3. But now we have 3 bonds and a lone pair. But our electronic geometry still has 4 areas of electron density, and so it's a tetrahedral geometry. And so tetrahedral geometry, at least electronic geometry, excuse me, equals sp3. We'll talk about that with the table in a little bit too. Now oxygen, we bring 1 more electron in the fold. Now we only need 2 hydrogens. We're just going to make water here. We make our sp3 hybridized orbitals. We're still just mixing up the 2s and the 2p orbitals. We're using all 3 of the 2p orbitals, the 2s orbital. So we get sp3. So we get 1, 2, 3, 4 hybridized orbitals. And now 2 of them are full, which means oxygen has 2 lone pairs. And 2 of them are half full, so oxygen is going to make 2 bonds, and so makes a bond, no hydrogen, bond, no hydrogen. And this could be a carbon over here if they're single bonded. This is what it's going to look like. It could be something else over here, nitrogen if they're single bonded. That's what it would look like. It'll get a little bit more complicated with double bonds here in a minute, but this is the basic idea. So we're just remixing these atomic orbitals. We're taking our valence electrons and we're just reshuffling them into these kind of intermediate energy level hybridized orbitals. And again, it does work. It works okay for the geometry. But as we carry through here, we can see what happens when there are double bonds. And so this is a different approach. So here's what happens. We don't use all of our orbitals. So we can have sp3 hybridization, or we can have sp2, or we can have sp. And those are all of our options with just regular octet rule stuff. So anything in the second row, this is how they'll behave. And so we'll have our 2s and our 2p, they remix, and in this case we're going to have a double bond. We're going to talk about what that double bond means in a minute. And so we're going to have an sp2 hybridized carbon because there's a double bond present. And the way you'll ultimately think about this will probably be a little bit reverse of what we're showing here, but just to kind of show. So what we're going to do is we're going to take 2 of these 2p orbitals and this 2s orbital, and we're going to mix them up. And so we're only going to have 3 hybridized orbitals, and then we're going to have 1 p orbital that we leave completely alone. And then we just fill in. We go electron, 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 and there's 1 electron in the unhybridized p orbital. So they're all still half full for carbon. Okay. So for oxygen, again, we just remix the same way. We're going to get sp2 orbitals, and we have 2 that are full, so we'll still have 2 lone pairs, and then we'll have 1 that's available for a single bond, and then we have an unhybridized p orbital. Now this p orbital that's unhybridized is going to be where our double bond comes into place. So double bonds are a little bit tricky. Okay, so this is what the geometry looks like in 3D space. We've got a carbon, we've got our oxygen. These are both sp2, so they have 3 hybridized orbitals. They are 120 degrees apart. They are a trigonal planar geometry, both of them. And these 1s orbitals over here, the hydrogens, will just come in to fill out the carbon. So we're going to make CH2 with a double bond to an O. Okay, so here's how the double bond forms. So first we get a single bond. We get this sp2 overlapping with the sp2. That gets us a single bond, which is also known as a sigma bond. So it's like a Greek S, so sigma. These p orbitals, this is a single p orbital over here. This is a single p orbital over here. Remember, they have that peanut shape. So there's part of it that's up and a part of it's down. So there's 1 electron that's floating around between this orbital, top and bottom. Could be anywhere in here. Same deal here. Well, when these sp2 orbitals overlap to make the single bond, these p orbitals aren't being drawn to scale. They're going to be very kind of much larger, and they'll actually have a region of overlap with each other as they stick up here and stick down here. And that region of overlap gives us a space, according to valence theory, if they're valence bond theory, if those orbitals are overlapping, they can share electrons, they're going to form a bond, and we get what's called a pi bond. And so this is the top half, and this is the bottom half of a second single bond, but this is the one that gives us the double bond. So we see we have a carbon-oxygen double bond here. This is what it looks like according to hybridization theory, and actually this is pretty accurate for what it looks like in general. So you have half of the bond above, half of the bond below, and so there's a couple interesting features here. So a single bond can freely rotate. A double bond cannot. It is totally locked in place, and so that gives us situations where you can have a different molecule depending on what's sticking out which way, because it can't freely rotate to look like the other one. But single bonds, it's like a car axle. It can freely rotate, but a double bond is not. There's a reason you don't have a double rotating car axle. It doesn't work. You can't. It won't spin. And so you have a single one, and you can rotate the entire molecule, but you can't flip this carbon. Not without breaking a bond and reforming it. So that's a chemical change. You would have to do chemistry for that. So there's a lot to unpack here. So make sure you understand what you're looking at with these images, because this is a very key idea. Now, if we were to have a triple bond, we would have a second unhybridized p orbital. So in this case, we have a double bond. We've got our single bond in the middle. That will always be the case. You will always have a sigma bond. It's like you've always got caramel in the middle of your Snickers bar, and then on the outside, you've got what do they got in those? Like there's like nougat and peanut and all that stuff in the middle, and then on the outside, you got the chocolate coating. Well, there's only chocolate on the top and bottom of this Snickers bar. But if you have a triple bond, what happens is you have a p orbital that's up and down, and then you have a p orbital that would be going front and back, and so you'd have an overlap 90 degrees from this top and bottom, right in the middle. That'd be coming out towards us and then back to the oxygen. It'd come off the carbon, away from us, and back to the oxygen. So you'd have 2 pi bonds and a sigma bond. So if you have a single bond, you have a sigma bond. If you have a double bond, you have a sigma bond and a pi bond. And if you have a triple bond, you have a sigma bond and 2 pi bonds. And those pi bonds are always going to be split in half. There's going to be half on one side, half on the other. And the orientation, just depends on how we're looking at it. But they will not, the 2 pi bonds will not overlap with each other. That's a key detail. Okay, so there was a lot there. Just hang in there. Rewind if you need to. I just talked about a lot. We're going to go to the last image now, and this is actually a table from your textbook, so 9.3. And you're probably wondering at this point, like, how do I know what hybridization I have? How do I know, how many sigma bonds are going to be in something? Well, the answer is just the steric number. You just want to go, what's my electronic geometry? How many electron groups are there? If you have 2 electron groups, and this is where it's great. You just count to 2, basically. You just go sp. That's 2 orbitals. You're done. If it's 3, spp, so we go sp2. That's 3 orbitals. That's your hybridization. And if there's 4, if you're using 3 p orbitals and an s orbital, which we showed with carbon and oxygen and nitrogen, that's sp3. So if there's 4 electron groups, and remember double bonds, triple bonds, those all count as one area of electron density. Those all count as one electron group. And let's see, so that's sp3. So you just go s, p, p, p. That's 4 orbitals we just named, so that's sp3. Now, 5 and 6, this is what happens when we have expanded octets. How do we expand octets? We're out of p orbitals, so we start bringing d orbitals in. So you can only count to 3 with the p orbitals, and then you start bringing in d orbitals. And so you have sp3d, that gets you 5 orbitals. And then 6, if you have a steric number of 6, if you have 6 groups, in octahedral electron geometry, then you have sp3d2, because that's sppdd. That's 6 orbitals we just named. So sp3d2. And then we stop there. We don't have stuff with 7 that we're, it probably happens at some point, but we're not worried about it. Extremely, whenever I'm like, oh, this thing never happens, I always open up like my chemical engineering news and find out that some crazy chemist somewhere has decided that they want to ruin general chemistry for everybody, and they've done something weird, and obviously we shall talk about it, and I fight back by ignoring them. You can take a higher level chemistry if you want to learn about how you get, a steric number of 7 or a quadruple bond or anything like that. Like, we're not going to worry about those things in this class. They effectively don't happen, but if you push stuff with lasers and diamond vices and do all kinds of weird stuff, then at really low temperatures or whatever, or really high temperatures, and really low pressures, whatever it is you need to do, yeah, you can get weird stuff to happen, but you can learn about that outside the class. I won't test you on it. All right. So again, there's what these things mean. So SPE means we have 2 unhybridized p orbitals, and then these purple groups right here, that is our sp orbitals. And that means we're going to have a linear geometry because these p orbitals are going to be used to make a triple bond. This will be a pi bond overlap front and back. This will be a pi bond overlap top and bottom. And then we get a sigma bond in the middle. We get our single bond in the middle. And then this will either be a lone pair or it'll bond to a hydrogen or another carbon or whatever it might be. But we get a linear geometry at 180 degrees. And so this is all from before. This is all from the geometry portion of this chapter. So this is a big section, but essentially all it comes down to, I really want to make sure that this is clear. It just boils down to, first thing is, what is the hybridization? Well, you can go, well, what is the molecular geometry? How many steric numbers are there? And then you work backwards from there. So this is the new idea. You don't start here. You don't go, oh, it's sp2. You go, oh, there's 3 electron groups. It's sp2. Oh, there's, there's 4 areas of electron density. There's, maybe 2 lone pairs and 2 single bonds. Well, then it's sp3. And again, there's 4 orbitals here that we're counting to. You can only use an s orbital once. There's only one s orbital, and then you can only get up to 3 p orbitals, and then you got to start bringing in d orbitals. So that's the trick. All these bonds, these are all from the geometry section. All these names, these are from the geometry section. The number of bonds, number of sigma bonds, that's kind of a new idea, but that's essentially just number of single bonds. So packed in the middle of every double bond is a single bond. Packed in the middle of every triple bond is a single bond. Packed in the middle of every double bond is a single bond, and so on and so forth. And so you can have 3, you can have 2 of the lone pair, because you can essentially have a lone pair over here, a single bond there, double bond involved here, so on and so forth, and it just carries through. So we will leave it there. Again, if you have questions, just email me. Use the forum content. So this is a pretty long video. It looks like it's about 20 minutes. So you'll probably want to rewatch a few things a few times. Try to look these figures over. I'll have a worksheet to kind of really make it clear what you're expected to know out of this. Like, you're not going to be drawing these things by hand, but you should know what a pi orbital is, what a sigma orbital is, or sorry, a pi bond is, a sigma bond is, and that these orbitals correspond to the molecular geometries we've already learned, and how you can tell what hybridized orbitals there are based on the bonding structure, based on, the steric number, the number of electron groups or regions of electron density around a central atom. So I'll leave that to you. And if there are questions, email me, use the forum. Um, but take a shot at the practice sheet too, and just make sure. Maybe you feel like it's not making sense, but maybe it starts to once you go through it, and you can work on that and watch this video. So hopefully this will help you out.